The theory of linear algebras is a very basic tool to understand symmetry for elementary particles. And Dyson said because he was looking at the problem as a mathematician and not as a physicist, he missed the chance of actually understanding this. Now, there's a sequel to the story, as he related. During that time, that particular year he was looking at this problem, Professor Ian MacDonald from Oxford was visiting Princeton University and was also working on this problem. And both of them had their daughters going to the same school. And they saw each other quite often, but never talked about this. Right? Now, so I'm not suggesting that every time you take your kid to school, you talk to the guy next door and say, what problem are you working on? But just on the off chance that the person might be doing that. No, so the thing is that he said that if he had put his physicist hat on, or he had talked to Ian MacDonald, then things would have been different. In the end, of course, there was a happy ending, meaning that MacDonald actually worked out the whole thing himself and published the paper, of course, without Dyson's name. But Dyson's happy that this problem was solved. So here's another picture of him and Dyson. Now, there's one, I guess, something more significant when we talk about missed opportunities that actually happened in mathematics, which Dyson, I think, felt quite strongly about. In fact, here's Isaac Newton, and here's James Clerk Maxwell. Now, we all know what Newton did, right? Now, Maxwell published his paper on the laws of electromagnetism in the year 1861. That's 2 years after Riemann presented his paper in Göttingen on the Riemann zeta function. And therefore, it was 2 years after Darwin published his book. Now, the significance of that piece of work by Maxwell, as we look back today, I guess cannot be overestimated. In addition to providing the basic principles of the transmission of electric power and radio technology, he also laid down the principles of electricity and magnetism in its most general conditions, right? It gave an explanation, for example, of light as an electric magnetic phenomenon. But more than that, in the views of quite a number of people, including Dyson, Maxwell's achievements in electromagnetism actually was no less than what Newton had done in gravitation. The only difference, however, was that mathematically speaking, after Newton had published his work, Principia Mathematica, that gave the laws of gravitation and all the other things, maybe because of his preeminence, many mathematicians and physicists follow up on what Newton had done. So, for example, Euler studied what Newton had done and then looked at the theory of geodesics, and this was then followed by Gauss, who eventually introduced differential geometry, right? And then, of course, people like Poincaré, for example, also look at what Newton had done, then studied the question of orbits of planets and all that, and that eventually led to the discovery of what we call dynamical systems, chaos as we call it today. And topology, the study of topology was also a brainchild of what Newton has done in analysis and so on and so forth. So lots of mathematical developments happened after Newton's work. But for quite a while, in the case of Maxwell's work, not too many people, I mean mathematicians, actually follow up. Now, in the views of some people, Dyson in particular, if the mathematicians had looked at what Maxwell had done very seriously, Einstein's theory of special relativity, for example, would have been discovered much earlier than 1905. And then maybe even something like what is called hyperbolic differential equations, something like functional analysis are part of them. Topological groups, for example, would have evolved much earlier than when they did today or many years later. So Dyson, in his lecture, actually says that he believes that the progress of mathematics and physics had been, was retarded for many years because of, quote, the unwillingness of mathematicians and physicists to talk, right? And he said that, well, one of the reasons he thinks is that maybe there's a difference in personalities between these two people. When Maxwell gave a lecture to the British Association 9 years later in 1870, British Association is an association that promotes the unity of science, that kind of thing. And Maxwell talked about his electromagnetism laws and his discovery for electricity and so on and so forth. And then in connection with earlier work done by people like Gauss, Lorentz, and Euler. And Maxwell, after talking about the work of his predecessors and then the German school, as we call it, and then his own work, he just said that, well, an approach that I personally prefer is this, right? It's a very modest tone. Whereas if you look at Newton's book, the Principia, the very first sentence, he said, in this book, I lay down the framework of the system of the world. Okay, all right, okay. I mean, the sheer confidence itself makes you want to follow the guy, even if you don't know what he's talking about. So in that sense, I think psychologically, if someone is not so sure about himself, you probably want to follow him as a leader, even though he's done great work, right? You're not too sure, but so perhaps the personalities of these two people did have an effect on the outcome of what people, the development of the science. We don't know. Now, I want to then maybe to go a bit deeper into this to try to understand in what way do actually people who are involved in research, how do we actually look at things by considering what people know these, I guess, major mathematicians or physicists or scientists have done. What do they do? Of course, the first element of discovery, I would say, and everybody will agree, is creativity, drive and passion. This one has been, said over and over again, so I shall not dwell on it. Without that, you cannot even do research. So let's take it as given. Observation, I think, is quite important. There's a famous quotation that came from Pasteur, right, that says that in the fields of observation, chance favors the prepared mind. What this means is that, your mind must be there, so to speak. There must be some background preparation. You must have been thinking about a problem. You must have been working on that one, on the particular problem, so that when chance knocks on the door, you know when to open it, or that you should open it. So we look at the meeting between Montgomery and Dyson. That's an instance, an example of meeting the right person at the right time. Right? Here is an Another example of James Watson, you can get this thing from his book called The Double Helix, where he described the discovery, the work that led to the discovery of the structure of the DNA by him and Francis Crick and also Maurice Wilkins. And Watson mentioned in his book that, well, he was not really trained as a chemist. So he said that as an undergraduate, he tried to avoid taking chemistry and physics as much as possible. Anything that required hard work, he wouldn't want to do. But then he got interested in the structure of the DNA. And then in 1951, when he was about to start his postdoc work in Cambridge, he attended a meeting in Naples. And the first few days of the meeting were well, to him, very boring. Nobody said anything useful. There was a lot of hot air, according to him. Until this guy from King's College, Maurice Wilkins, gave his talk. And Maurice Wilkins' talk actually inspired him. At the end of Wilkins' talk, a few photographs of the X-ray diffraction of DNA were shown to the audience. And according to Watson, he was immediately excited. Immediately saw the relevance and importance of chemistry. And I guess that changed his life, maybe, right? Because at that time, how old was he? He finished the work on DNA with Crick and all that when he was 25. I think at the time it was maybe 22, 23 when he went to attend this meeting in Naples. So clearly he had been thinking about DNA. He wanted to understand the structure of DNA. The double helix thing, of course, was the eventual outcome. Oh, here the picture on the left is Watson, on the right is Crick, and behind them is the model of the DNA, the final version of it. Right? So here's another instance of how chance favors the prepared mind. Right. Now, here's another instance of how this so-called observation actually helps in discovery. In this case, it's mathematics by Henri Poincaré. Hadamard published a book called The Psychology of Invention in the Mathematical Fields. And that was a careful study of how mathematicians work and think. In fact, he also included an appendix, a letter from Einstein to him, in which Einstein described how he actually worked, what sort of thing he would look at when he thought about problems and so on and so forth. And in Hadamard's book, he referred to an article that Henri Poincaré was, along with David Hilbert, considered the two leading mathematicians around the turn of the century, 1900 and so on. And Poincaré gave a lecture to the Psychology Association in Paris, I think it was 1901, 1902, in which he gave himself as an example, analyzed his own thought process. And this was picked up by Hadamard and mentioned in his book. Now, Poincaré gave an example of his work on what's called Fuchsian functions. Today it's called, or later on it's called automorphic functions. We don't need to worry about what these functions were. Anyway, Poincaré was thinking about such functions, and then he was actually trying to so-called construct them to show that these functions exist. And according to Poincaré, for many days, he struggled with this thing and he got stuck. He had nowhere to go. One night, he had black coffee. It was the wrong decision, maybe, and could not sleep, right? And then somehow ideas just came up, good ideas, bad ideas, some lock in with each other, some just knock off, and so on and so forth. By the time he woke up in the morning, somehow all the things had come into place. And then the rest to him is just the details. So he just, spent about a week or so to write out the thing. Poincaré also gave another example where he was working on something subsequent to the discovery of the existence of the Fuchsian functions. I think he was trying to look at the structure, trying to come up with something that would actually describe the total picture of the Fuchsian functions. Again, he got stuck. Then he said, one day he went on a trip, or field trip or something like that. As he stepped on the bus, suddenly the idea came, right? Then he boarded the bus and started talking to the guy sitting next to him about something totally different. Right? In other words, he completely forgot about the problem that he was working on. But he knew that he had already had the solution, and after the field trip, he went home and then spent another week to write out the things. How he believed that it's not a good idea to always work on the same problem, thinking about it day and day night. You think about the problem and then put it aside, and after that, the subconscious will take over and think for you, right? In Poincaré's case, it worked. I don't know in our case whether it will work, but this is how it happens. I mean, when we try to understand the psychology of discovery, I think many of us with our own experience of one type or another, but what Poincaré has described is just really very fascinating, because he shows us that quite often really, you don't really want to work on the same thing, thinking about it day and day night, because you may actually make no progress, put it aside, and somehow, on autopilot kind of thing, somebody will work for you, right? So, but obviously, the reason I think that this worked for Poincaré was because he had a prepared mind. When he was looking at this thing, he kept thinking about these things, and then even subconsciously, when somehow one of these probabilities just happened, then he could immediately pick it up and got a solution. There was once, I think, an article, I think I remember reading, where Mozart talked about his discovery. To Mozart, it's something very different. Mozart, now in his mind, everywhere he looked at the musical notes, all he needed to do was just to pick this one up, pack that one, put them together, and you got a symphony. But again, I believe that this has something to do with the prepared mind, right? If you keep thinking about it, if you're ready for that when the time comes, it will really hit you, and then you've got it. Now, another key element, I believe, is courage. Now, courage is here in the human sense and in the scientific sense. I will just give, okay. Here's one example. Kurt Gödel, born 1906, died 1978. He was a major figure. Well, I guess he's one of my heroes since the really first person to have done fundamental work in the field of logic. And Hilbert, as I mentioned earlier, in the year 1900, when he proposed 23 unsolved problems that he believed the solution would change the face of mathematics, proposed the first problem is what we call continuity hypothesis, but the second problem has to do with consistency of mathematics. In other words, everybody, including Hilbert definitely, believed that mathematics is consistent, mathematics is complete, meaning that if you start with the right axioms, eventually you prove everything in mathematics. Done. Then computer can take over, and then I guess mathematicians will lose their job. Now, for a long time, this was the belief, and Hilbert and his school, many of his students, they actually pushed in this direction, wanting to get the ultimate version that would prove the completeness of mathematics. Along with that, also to prove that mathematics is consistent, meaning that it will not one day lead you to a situation where you actually prove 1 + 1 is equal to 3 or 4. Or something like that. Now, Gödel in 1931 actually showed that these two aims were unachievable. So he showed that mathematics is inherently incomplete. There are some facts about mathematics which you can never prove, right? And then, and one of the facts is that if mathematics were consistent, you can never prove that it's consistent. Okay. Now, this takes a lot of courage because, first of all, Gödel was a nobody, right? Just coming out. Hilbert was a giant at that time. So psychologically and mathematically, it was indeed an uphill task for him to do this. And so what I'm trying to say is that, you know, if especially the young men in the audience, young women, that if you know, think that you have hit on some really bright idea, right, and your supervisor says it's a stupid idea, prove him or her wrong, right? Now, it takes a lot of courage. It's not easy, right? Your paper may not be accepted, for example, okay? Your work may be ignored for a while. And it's not an easy thing. I mean, it's easy for us to say that, but it's not, you know, something that just say we'll do it. So courage, I think, is an important component to make discovery, especially important discoveries in science. There's another example that I don't have slides here. George Cantor, the inventor of set theory, when he introduced the idea of set theory and so on and so forth, he encountered strong opposition from very established mathematicians, including Poincaré. Poincaré actually said that later generations of mathematicians will come to realize that Cantor's set theory was a disease, and we have recovered from that disease. And it was so traumatic that Cantor eventually, he died in an asylum. So when I say courage, in the human and scientific sense, it is something that you know, those who have experienced that will know. Those who have not will one day know, maybe. Right. Then there's, I call inspiration. Inspiration, I think I have alluded to this earlier. For example, Watson attending a lecture by Wilkins, and that is a form, a kind of inspiration. You suddenly realize that something is very exciting, something really worth doing, something that you want to learn more, and so on. And then timing. Timing, sometimes we call luck, right? Timing is always there. And then when your timing is right, you may not know. But when your timing is wrong, you actually know. Here's an example of Galois. Évariste Galois was, I would say, you know, again, a genius mathematician. As you can see, he died very young, 19 or 20, in actually a duel, right? During the French Revolution. He had come up with something really, really original. Today we call group theory, right? He wrote the manuscript, he sent it to the French Academy, and the manuscript was rejected. Here we talk about courage again. And very soon after that, he was involved in something silly, right? And then ended up agreeing to engage in a duel with his opponent the following morning. The night before that, he wrote out a number of many pages of mathematics that he wanted to send his friend, and at different parts of his manuscript.
I think he was 20, not 10.
20s? 10?
He's only 10 years old.
No.
Remember, I read his story.
Cannot be.
Yeah, he's 20. I think
20.
he was 20.
20.
He
Typo.
love affair and duel.
Yeah. And he wrote saying that I have no time, there's not enough time for me, right? Now, the timing for him was wrong, right? As people realized later, he was at least 10 to 15 years ahead, mathematically speaking. His discoveries, even after that, you know, the manuscript was sent to his friends. Some people look at it, many people didn't understand what he was talking about, right? So timing has to be right. And timing, on the other hand, you know, if you're ahead of your time, what can you do, right? God is not on your side, maybe. But it's unfortunate. I mean, timing you cannot control, right? I mean, very few people are willing to hide the manuscript for 10 years and wait for the right time. How do you know when is the right time, right? So Galois was perhaps one of the unfortunate historical figures, in the history of mathematics, but he's not the only one actually. Wolfgang Doblin. He was actually a person of German origin, but ended up as a French citizen. I guess because maybe the family moved to France and so on. And then he actually fought in the Second World War for the Germans, right? But I think he realized that there's some problem there, and he actually committed suicide. In the year 1940, he was at the war front. He sent a paper again to the French Academy called on what? On the equation of, I forgot the exact title now. Anyway, in which he laid out the idea of what we call today something like what is something understood to be Ito calculus, that studies the part of Brownian motion and then do integration and so forth. Ito calculus allows you, I got it from my colleague, that to integrate functions which are everywhere non-differentiable, right? Brownian motion, and then when he did Kolmogorov equation, yeah, I think that's the title, on Kolmogorov's equation, and when he did this, as you can see, he was very young. Now, why was the name associated with Ito? Well, Ito did this a few years later, also as a young man, in Japan, however, right? And of course, now the theory is called Ito calculus, and for a while anyway, it was a major tool that's used in financial analysis, stock market and all that. Well, we think that the mathematical theory is still sound, but maybe the people who applied that had some problem. Okay, but Ito did this work when he was working for the Ministry of Finance, I think, or Foreign Affairs in Japan, almost like Einstein working in the patent's office. Statistical Bureau, was it? Not finance, okay. Statistical Bureau, right? He was not even a professor, right? He was just a nobody, and so on and so forth. So here we have this timing thing. Now the manuscript was sent to the French Academy, but it was not open until the year 2000. All right, and suppose it had been open immediately at that time, we don't know what history would say today, right? Was it a question of timing, or was it a question of what? We don't know. But here is another example of chance, that's something happened beyond your control. Okay, so what can we draw from, I think my time is up, right? This is my last slide already, right? From all these things. Well, first of all, we can learn it from what Hadamard had said in 1944, that for him, who wants to discover, right, he should not confine himself, or herself, I think we should say, right, to only one chapter of science, but to really to avail himself, keep in touch with many other chapters in science. But when we talk about chapters in science, you can actually be more specific, right? If you work in chemistry, in mathematics, or whatever, of course, in the multidisciplinary world of today, it is certainly important, and we have seen examples of that, to know other science